Hello everyone, welcome back to today's class. As we were discussing in our last class, we were talking about transistors. We were talking about, in particular, P and NPN transistor, and we were focusing on the three gates, the base, the emitter, and the collector. So basically, as we were saying, is we need to know only a couple of equations. We don't need to know a lot of equations. These are the only couple of equations that you would be needing. But these are the three modes in which they operate. This is the small signal analysis that we will be focusing on. But before I move on, let's start with the basics. What is a BJT and why do we need it? Let's answer that question. In order to answer that question, let me just start with a basic understanding of a BJT. So a BJT, basically, as I mentioned earlier, it can work as a switch. Or it can help as an amplification. When I'm talking about amplification, I'm talking about current amplification. That means whatever input current I'm applying, my output current would be amplified by a particular magnitude. A BJT has three gates or three parts. One is the base, the other is the collector, and the third one is the emitter. When I'm talking about input current, I'm referring to the base. When I'm talking about the output, I'm mostly referring to the collector current. So when I'm saying it helps in amplification, that means whatever is my input current has been amplified by a particular amount to give my output current. That's the bottom line. Okay. That magnitude is actually represented by beta. So if I say my beta over here is 100, and my input current is suppose 1 milliamperes, my output is multiplied by 100 times, it would be 100 milliamperes. Okay, that's the bottom line. So, and that is actually represented in our first equation over here. Not necessarily in our first equation, but it's on a second equation. So as you could see over here, this is my output current. It's been multiplied by this factor beta, which is my magnitude for amplification, into my input current. Now my emitter current over here is, if I apply Kirchhoff's current law, let me pull this up again. If I apply my Kirchhoff's current law at this end, at this node, this is my one current, this is my another component of the current. So if I apply KCL at this node, I can definitely write IB plus IC equals IE. So that's how I basically get this equation where IE is nothing but by applying Kirchhoff's current law, I'm getting the base current and my collector current. So I just summarize, a BJT can act either as an amplifier or it can act as a switch. Right now, we are focusing on its amplification property. As I suggested, my input current is my base and my output current is my collector current. And by what magnitude is my input current magnified is actually represented by beta. So whenever I multiply my input current with a factor of beta, I'm supposed to get my output collector current. Okay, and my emitter current is nothing but, if I'm applying KCL over here, is the sum of my two currents, IB plus IC equals IE. Usually, not usually, almost 1000 times, like all the time, you would find that your IB is obviously small, right? Because it has to be amplified by a particular factor. This factor could be as high as 1000 or 100 times or whatever value it is. So we can approximately say my IE is almost equal to my IC. Almost, not exactly equal, but almost equal to my IC. However, uh, if you want an exact and precise value of that, you can multiply it with the factor of alpha. If you're wondering what alpha is actually can be derived from beta itself. So beta divided by beta plus 1, and that will give you alpha. So that's how you can figure out your alpha. And you can either assume IC is very close to IE, you won't be too far off from the real value. But if you want a precise value, that's how you can figure out by what factor it needs to be multiplied to get an exact value. However, at times your IC might not be given to you and you're trying to figure out IC. So IC is nothing but the saturation current of this emitter over here multiplied by an exponent of the base BE, which is obviously you can assume as 0.7. Unless a different value is given to you, you can assume it's 0.7. And VT is the thermal voltage. For those of you who are not familiar with the previous videos, you can just watch your previous videos, or it's given over here. Your VT is actually nothing but 0.026 volts. So an exponent of 0.7 divided by 0.026, whatever you get, you just multiply with by saturation emitter current and you would be able to figure out your IS. I hope I made some sense over here. Now, once I did make some sense over here, if you're trying to figure out how a PNP and an NPN transistor differ from each other, it can be represented by this diagram over here. As you could see over here, for a PNP transistor, it is pointed towards the base, PNP. An NPN transistor, it will be pointing out towards the emitter. So that's how the notation differs for a PNP transistor and an NPN transistor. Okay. And now coming back to another important point, its mode of operation. As I said, it operates in three modes. It can either operate in a cut-off region, it could operate in a saturation region. So when I'm talking about this acting as a switch, that means I'm focusing on is either working in my saturation region or is operating in my cut-off region. Okay, what do I mean by that? So if I'm trying to explain it, so if I have a transistor, when I say it's in the cut-off region, that means it's working as an open circuit. That means it's not working at all. This is the cut-off region. When I say it's in the saturation region, it's like this. It's like a short circuit. So whatever is coming in my base and collector is in my emitter. It's like a short circuit. Okay, so when I say it's the switch, that's either on or off, on or off, on and off. So that means when I say it's a switch, it's either in the saturation or in the cutoff region. Now, when would it be operating in my cutoff region? It would operate in a cutoff region if I'm not applying enough voltage across my base and emitter. Typically, I need to apply at least a 0.7 volt. I need to apply at least a 0.7 volt across my base and emitter for it to actually conduct and operate either in the saturation region or in the active region, which we will discuss shortly. But if I'm not applying that minimum 0.7 volts, it would be in the cutoff region. So it's like assuming there's no transistor at all. Now, once I start applying that voltage, at least above 0.7 volt, it would be either in the active region or in the saturation region. So if I'm trying to draw an active region and saturation region, the difference is in an active region between a collector and a base and an emitter, you can assume it's like a variable resistor. The resistance would slightly vary. But once and saturation from the name itself, once it reaches a fixed value, it becomes in the saturation region. Okay, so once it reaches a fixed value, it would be in the saturation region. At that time, we can assume it's a short circuit. Okay. So these are the three modes of operation: cut off, saturation, and active region. You don't have to worry. Mostly in most of the exams, it would be actually given in your saturation region. So you don't have to worry about too much. Now, coming over to AC signal analysis. So this was the DC signal analysis, okay, which we call the large signal as DC circuit analysis. However, when you're working with AC signal analysis, the BJT over here, so for an active region, you can actually represent it by, since I said it's a current amplification, right? So you can multiply with beta and IB with input current, and you would be able to represent it like this. However, at times, you would realize that if you have an AC signal over here, this is your diagram. Okay, this is your pi model. I think it's called the hybrid pi model. So what you can do is this region can be represented like this. So let me just use this image. Can be represented like this, where this is your base, this region is your emitter, and this is your collector. Base, emitter, and collector. Now, what you have to know over here, this is your R pi. This is your, instead of this, you're using this. Okay, so you're just changing it from beta IB to GMVBE. And the emitter stays at this. Now, R naught, if you're trying to figure out how much is the R naught, this resistance, output resistance, is nothing but VA divided by IC. Okay, so this values will be given to you. This is the early voltage. Okay, this values will be given to you. We won't discuss too much because I don't want to confuse you guys. But this values will be given to you, the early voltage, and this is your IC in the Q point. Okay, the collector current at the Q point. This values will be given to you. So if I divide my voltage with my current, I can obviously find my output resistance over here. If you're trying to figure out my GM over here, GM is nothing but this collector current divided by VT. Now VT, as we just discussed earlier, it's 0.026. So once you know your output collector current and you divide it by 0.026, you would be able to figure out your GM over here. Your VB is given, like would be given to you. This R naught, you just figured out how to figure out this parameter. If you figured out this parameter, you figured out this parameter. The only thing that you're left with is on input side R phi. Now this is basically figured out by beta, the beta that we were discussing so far over here, divided with my transconductance. So once you figure out beta by GM, I would be able to figure out this resistance. So that's how you figure out all these three parameters. So as I said, to summarize, small signals analysis is nothing but if you have an AC signal applied to a transistor, it's not too straightforward like this where you only have DC signal. Your BJT needs to be replaced by a hybrid pi model, the one over here. And let me take another snippet too. You have to replace it with a hybrid pi model like this. Your BJT would no longer, you cannot use like this. You have to convert it into a hybrid pi model. Once you do that hybrid pi model, you would be basically able to figure out these parameters from the three equations that we just discussed earlier. Okay, so I think like this is the only things that you need to know about BJTs. Before we move on to MOSFETs, let's just recap what we studied today with some couple of questions. So right now I will stop sharing my screen and I would pause my video. So let's start by our first question. As you can see over here, you have been given this circuit diagram where this is your base, this is your collector, and this is your emitter. The beta is given to you as 100. Your RE is 2 kilo ohm. Your RC, because it's connected to the collector end, I'm calling it 2 kilo ohm as well. You have a DC voltage over here, another DC voltage over here. So you don't have to worry about AC signal analysis. All they're asking you is how much is the voltage across this one? And how much is my IE? Okay. So it's a difficult question. So how about I give you guys 10 minutes? So I'm going to pause the video and I'm going to pause the screen. And after 10 minutes, we'll try to discuss the solution. Okay, so coming back to the solution. Now, this is a very straightforward equation. So the first thing what I would suggest you to do is basically replace this one with a circuit diagram. So you had a BJT. Okay, just try to replace those with a circuit diagram. It would be much more easier for you to figure it out once you have it, something like that. So now the first thing over here was just making sure that I have the right question. We stop the share. Okay, so yeah, so this is the right solution. So this is what we need to focus on. So over here, basically what they applied was they basically applied KVL over here. Okay, so when you apply KVL over here, on this end, as I said, you need to apply a 0.7 voltage drop across this one for it to function. So you have a 5 volt, then you have this multiplied with my IB, then you have a voltage drop across this one, and then you have IE, and you multiply with IE. Now, as I said, IE is nothing but IC, right? Right? So over here, they took 101 over here is because we know IC is beta IB. Okay. So since this is given as 100, okay, so once you plug in the values over here, you're supposed to get your IB. And this is, you're trying to get this because you have just one equation. So you can afford to have only one unknown. So what they're trying to do is they're trying to replace this IE with IB. Okay, so now so your first step would be from this equation to figure out your IB. Once you figure out your IB, you can pretty much figure out your IC because you just multiply with 100. From there, you can pretty much figure out your IE as well because IE is nothing but alpha, IC divided by alpha. Okay, now coming back, once you figured out that, now your next thing is basically to figure out the collector to emitter. Then you apply a KVL at this end. Okay, at this end of the equation, of the circuit. So 10 minus my VC, you pretty much know IC from here, and it's 2K. So if you know VC, if you know IC, if you know 10 volt 2K, you can pretty much figure out your VC. So now you know your VC, right? And E, so what you did was you applied like the potential difference, VE minus my ground, because it's connected to the ground, divided by my 2K. So I can pretty much figure out my IE. So once I know my VC, I know my VE, so I can subtract VC from VE to get my VCE. Hope you understood this equation. It's a little complex, but once you understand it, take some time, you'll be able to figure it out. Hope you understood it. Thank you. That's all from me today. Have a great rest of the day.